So what we're going to be learning about in chapter 11, we're going to start learning about probability. And the reason we need to learn about probability is because then in turn, in chapter 12, we will be studying some of the basics of statistics. And it turns out that that's just what this course is all about. We study a nice hodgepodge of different mathematical ideas, of different mathematical things. So let's start off. It turns out in order to do probability theory, you actually have to learn how to count. And I don't mean count on your hands. Count the number of apples you have in your grocery cart at the Walmart. We're not talking about counting that's simple like that. Anybody can do that. What we're talking about is more complicated counting, where you have to count things that could turn out to have large numbers of things. And it's actually, believe it or not, incredibly, insanely difficult. So let's motivate this with a lead-off example. Let's say you're dining out, maybe not since COVID-19 has hit and restaurants are weird, although you can maybe go sit on the patio or something. But let's say you're dining out at your favorite restaurant, which of course is Chili's. All right, I don't know about you, but Chili's is awesome. They got that skillet queso. And it's just amazing. It's a wonderful dining experience, great food. It's just something you should really do a lot, as much as you possibly can. And once again, I'm going to make this joke, and I will make this joke until the day I die. Am I being paid by the Chili's Corporation to advertise for them to y'all? Yes, I am. And that's actually not true, but it's a fun joke to say. So let's say you are planning to have a 4-course meal. You're planning to have a 4-course meal. An appetizer. And even before that, you might, or you can, at the same time, you can order your drink. You can have your actual meal, or sometimes it's just called your entree. That's your main dish. And then also, you can have a dessert. Let's say you're treating yourself. You're going to treat yourself this evening. So let's break down the numbers. Let's say there's 8 different appetizers that you can choose from. Let's say there's 8 appetizers. They have the skillet queso, but they might also have like an appetizer sampler thing. And then they might have, you know, some nachos or some wings. Now, drinks are weird because you have all the sodas, but if you start to really get into like possible alcoholic drinks, if you're, you know, 21 and up and can do that, you can get into a lot of really funky drink combinations and choices. So, I mean, there could be, I'm going to put it at 50, but really you could actually choose like, I bet a bartender could make thousands of different drinks from the different things there. So 50, we're just kind of limiting ourselves a little bit. The entree, let's say they have 24 different entrees available, and they have 7 possible desserts available. How many different 4-course meals can you have? How many different ways can the 4-course meal look to you? We're actually going to multiply here. We're going to take the number of appetizers. We're going to multiply that by the number of possible drinks you could order. So apps, drinks, then your number of entrees, the giant or otherwise, and then the number of desserts you could have. We're going to take the amount in each and we're going to multiply them all together. So let's think. We have 8 appetizer choices, 50 drink choices, which that might even be a bit of a low ball. Entrees, you might have 24. Desserts, you might have 7. And now what we're going to do is we're going to multiply all these together. 8 times 50 times 24 times 7. Of course, you can use the calculator for that. I wouldn't try to do that in my head. There's no need in most cases. So 8 times 50 times 24 times 7 is 67,200, which is a lot. That's the number of different kinds of 4-course meals you have where you constantly change at least one part of the meal from what you had the day before. Now, here's a good question. If you were to go to Chili's every single day, now would I suggest you go to Chili's every single day? Yeah, of course I would. You're going to get a different experience each time. The food is delicious and it's pretty cost effective. It's a pretty reasonably priced restaurant for a sit down place. So yeah, go to Chili's every single day. All right. And every day you go to Chili's, they give me 10 cents off of, whatever you spent. That's not true at all. Anyways, if you were to go to Chili's every single day and try a different 4-course meal, it would take over 184 years to try them all. If you went once a day. That's a lot. That's a lot of options. Now, most of us will not live to be at least 184 years old. I will, but that's just because of certain gems I've found that have been imbued with certain powers. I don't want to go into it. But anyway, that's nonsense. All right, got to turn off the nonsense, Josh. But anyways, that is what you can do. You can say it takes 184 plus years to eat every type of meal. You go once a day. So maybe she could be going 2 or 3 times a day. All right, that's cost effective. So interesting idea. So why did we know to multiply them all together? That's kind of the crux of it. Why didn't I just add them together or something like that? Will, partner, let's look at the fundamental counting principle. The fundamental counting principle. Now, what it says is if you can choose one item from a group of M items and a second item from a group of N items, then the total number of 2 item choices is M times N. Again, imagine you were this person here, and let's say, like most males, you had 2 pairs of pants and 3 different shirts you could wear. You could wear blue pants or black pants, and then you have a gray shirt, a yellow shirt, or a blue shirt. There's 6 possibilities of different outfits you can make for the day. First, there's 2 pant outfits times 3 shirt possible combinations. And it's 2 times 3 because once you pick pants, then there's 3 shirt options. But then there's a second set of pants. So that's just adding 3 to itself twice, which is just the same as multiplying 2 times 3. So the fundamental counting principle is really kind of just intuitive. It kind of just goes to the basic concept of multiplication for why it works. So let's say you have a restaurant that offers 6 apps and 14 main courses. If you want a 2-course meal, you just take the 6 times the 14, which is going to be 84. So there's 84 possible 2-course meals you can have at this place. If there are 3 options, if you have put on a pair of pants, but also you had to pick a t-shirt and pick a pair of sneakers, you would actually, and you have 2 sneaker choices, you would do 2 times 3 times 2, 2 pairs of jeans times 3 t-shirts times 2 pairs of sneakers. And you'd end up with 12 possible outfit combinations. Now, in reality, most of us might have more than 2 pairs of pants, more than 3 shirts, and more than 2 sneakers we could wear. But to draw a diagram of that situation, I mean, you could be looking at thousands of possible outfits from that. And so it's not practical to draw a diagram. So for the diagram's sake, we have to kind of keep it to a smaller number. But that's just how it works. So this fundamental counting principle can be extended. It says that if you have to complete a series of tasks and you're doing all of the tasks, then the total number of ways you can complete all the tasks is to multiply the number of ways you can complete each individual task all together. So let's say you're looking at, you're planning to take 3 courses, a math course, an English course, and a humanities course that you need, maybe anthropology or something like that for humanities. Assuming, you know, there's no scheduling conflicts, how many different 3-course schedules are possible? Well, you take the 8 math course choices you have, times the 5 English course choices that you have, times the 4 humanities course choices that you have, and you end up with 160 possibilities. 160 possibilities. So pretty simple concept. We're just multiplying each of the individual tasks, the number of ways we can complete each individual task, times each of the ways we can complete the entire task all together, and that'll give us that. Let's think of an even cooler possibility. Let's say you're taking a multiple choice test that has 10 questions. Each question is going to have 4 possible answer choices, and there's only going to be one correct answer. There's only going to be one correct answer. If you decide to just maybe answer the test at random, you have no idea what the answers are, and you're just going to choose at random, how many different possible ways can you fill out the test? Well, for question 1, you have 4 possible choices you can pick. For question 2, 4 possible choices. For question 3, and so on and so forth. So you're multiplying the number 4 to itself 10 total times in that particular example. Since the number is the same each time, we can express that in exponential notation of just 4 to the 10th power. And so for a simple 10-question multiple choice exam, where each question has 4 possible answers. So we're not talking about anything that's wild or out there or seems like it could generate a lot of different possible ways you can answer the entire exam. Actually, there's over 1 million different ways you can answer that exam. That is not an exaggeration. Go put 4 to the 10th into your calculator, and you'll see that's the case. So that's huge. That's a big deal. There's 1,048,576 different ways you can answer the test. Now, each problem only has one correct answer choice. So the number of ways you can answer the test correctly and get a 100 on all of them. So maybe we'll have fun with that. The number of ways you can get every question right, aka a perfect score on the exam. Well, think about it. The first problem only has one correct answer, times the second problem only has one correct answer. So you're just multiplying 1 to itself 10 total times. You can say that's 1 to the 10th, but that's really just 1. You keep multiplying 1 to itself, you just get 1. So what we're very quickly going to end up doing with this is we're going to say you can only get a perfect score 1 chance out of 1,048,576. So if you're random guessing on the test, there's only a 1 in 1,048,576 chance you'll get them all right, which is near impossible. That's if you're random guessing. Obviously, if you study and you know what you're doing when you walk in and you have pretty good confidence, you have a much better chance of getting 100 than that if you really know what you're doing. But if you're just shooting in the dark, you're basically not going to get a perfect score. Now, to calculate the probability that you'll get a passing score of, say, 70 or higher, that requires a little bit more mathematical heavy lifting that we're not ready to do just yet. But that would also still be a low chance, although it would be much better than the chance of getting a perfect score. So that's how probability is going to work. We're going to calculate the number of ways something could go our way divided by the number of ways something can go, period, whether we like it or not. That's going to be what we say is our definition of theoretical probability. So fascinating stuff. Let's calculate the number of possible telephone numbers there are in the United States. So telephone numbers in the United States begin with 3-digit area codes, followed by 7-digit local telephone numbers. Now you understand, when I was young, we used to just have 7 telephone digits in our number. Yeah, when I was growing up until like sometime in the early 2000s, they were just 7-digit telephone numbers. But it turns out we were running out of phone numbers because a 7-digit number, you can only create so many unique or different telephone numbers out of that. So we had to add area codes to the mix to create a much higher pool of telephone numbers to choose from. So area codes cannot begin with a 0 or 1, as well as the local telephone number cannot begin with a 0 or 1. So the number of area codes possible, which are 3-digit, well, there's only 8 choices for the first digit because that has to be 2, 3, 4, 5, 6, 7, 8, or 9. And if you count that on your fingers, that's 8. But then all 10 possible digits are available for the second. All 10 possible digits are available for the third digit in the area code. The local telephone number, same thing, only now there's 7 total digits, but the first digit only has 8 possible choices because 0 and 1 must be excluded. So the number of telephone numbers we can make, period, we can do 8 times 10 times 10 times 8 times 10 times 10 times 10 times 10 times 10 times 10. It blows up really quickly. We see that there's 6,400,000,000 possible phone numbers we can make in the United States. Now, right now, today, the United States has anywhere between, I would guess, 350 to 400 million people. The 2020 census, unfortunately, didn't quite go down as much as we had hoped because of the pandemic. So we're not quite sure, but the number, it's likely to be somewhere between 350 and 400 million. And there's 6.4 billion possible phone numbers that we can make in the United States. So it looks like we're not going to be running out of possible phone numbers anytime soon. Now, if you were curious, before area codes, this is the only digits you'd be multiplying together. Before area codes, and now we can see why they were needed. Before area codes, you would just do 8 times 10 times 10. You would only multiply 7 total digits together. And so 8 times 10 times 10 times 10 times 10 times 10 times 10. You'd realize there's only 8 million possible phone numbers before area codes. And I mean, even though it's called the local telephone number, you could still call it long distance. And so you could do that, but we'd be running out of phone numbers really quickly. We'd be running out of phone numbers really quickly. So you can see why we needed to expand. 8 million sounds like a lot, but there's now almost 400 million people in America. When they made the switch, there was probably at least 250 million people. So yeah, we needed more phone numbers, especially with the advent of the cell phone and so many more people having individual phones instead of just, well, we have one phone for the whole household. That's how it was when I was growing up. And I had to talk to my little church friends and church girlfriends I had on the telephone on Sunday afternoon, and my parents would be in the other room. and they could probably have picked up another telephone and listened to me on my phone call as we talked about, I don't know, Pokemon or whatever I liked as a kid. So Pokemon. I'm going to tell you guys right now, if Minecraft had been around when I was a kid, I would have been majorly into Minecraft. And the reason I know this is because now, as a 31-year-old man, I'm majorly into Minecraft. I don't get to play as much as I'd like, but I mean, I've been playing Minecraft almost since it launched 10 years ago. And, you know, I'll play it for like, I'll get really into it for about a month. And then I'll kind of say, okay, I need to step back because there's only so many times I can make, you know, a working Batmobile in Minecraft. But I have done it. Am I proud of that? Yeah, anybody would be proud of that. Making a working Batmobile. Yeah, that's called living the life. So we can use that fundamental counting principle in a lot of different ways. You can use a fundamental counting principle to calculate the number of possible passwords that you can have for a given website. And so if you think about it, I mean, you don't have to get too creative. If a password on a website, if you can use a lowercase letter of the alphabet, an uppercase letter of the alphabet, and we're going to count those as different. So a lowercase a and an uppercase a are counted as two different digits or whatever in a password. If you could also use any of the 10 numerals, 0 through 9. If you could also use certain, you know, exclamation mark, the @ symbol, the pound sign, excuse me, the hashtag for you younger ones out there. If you can use all those different digits, you can really quickly make a possibility of having trillions, if not more, possible passwords. I mean, even quadrillions, which is 1,000 trillion. You can make so many possible passwords that theoretically, that is a security measure that's going to keep evil hackers out from being able to get into your accounts because they can't possibly guess all the passwords that are possible because there's so many, it would take many, many lifetimes to be able to guess them all. Now, that doesn't mean that hackers and whatnot have not developed more advanced tools for breaking into stuff. We still hear about security leaks all the time, but that's theoretically why you're protected with a certain complicated password. It's also why most websites and whatnot want you to create complicated passwords so that it makes it harder and harder to break in. I just heard something that sounded like a snake hiss. I bet it was just a file dropping or something. Weird sound. That kind of freaked me out. Okay, so anyways, I don't think there's a snake down here, but if there is, I am a parcel mouth, so I might be able to communicate with it. Okay, so we've talked about the fundamental counting principle, and we see that there are indeed times when we need to use the fundamental counting principle in order to count things. But there's also things called permutations and combinations that we might need to kind of get involved with. And so let's talk about those. These are still counting techniques, just like the fundamental counting principle is. So let's define a permutation. A permutation is an ordered arrangement of items that occurs when no item is used more than once, and the way that you can order it is important. The number of different ways you can reorder the items is important. It's valuable to the context of whatever it is you're talking about. So let's think a permutation. Well, let's say that you were the classic example. Let's say you were arranging 7 of your favorite books on a small shelf. Well, there just so happen to be 7 Harry Potter books. Maybe those are your favorite 7 books. Now, you might think, well, why would I want to count the number of ways I can order them? Obviously, I'm going to order them. The first one will be the Sorcerer's Stone, aka the Philosopher's Stone worldwide. The second one will be Chamber of Secrets, then Prisoner of Azkaban, then Goblet of Fire, then Order of the Phoenix, then Half-Blood Prince, then the Deathly Hallows. Of course, I'm going to put them in the correct order. But let's play pretend and say you wanted to count the number of ways you could rearrange those 7 books, those 7 objects on the shelf. Well, for the very first spot, before you put anything, the shelf's empty. For the very first spot, there are 7 possible things you can put there. any one of the 7 books. Now, once you've picked that first book and put it on the shelf, now the number of possible things that can go into the second spot is only 6, 1 less than before, because we've already put something down. Then once you put 2 books down and you're trying to fill the third spot, there's only 5 things you can put into that third spot. And then you can quickly see that it becomes 4, 3, 2, 1. And then because of the fundamental counting principle, we multiply all of those together. 7 times 6 times 5 times 4 times 3 times 2 times 1. You don't have to do it in your head. You don't even have to do that on paper. Bust out your calculator. You can multiply those numbers very quickly, and you'll get 5,040. So there's 5,040 different ways you can arrange the 7 Harry Potter books. Now, if you wanted to find the number of ways you could arrange the Harry Potter movies, if you had each of them in their own Blu-ray or something, there's actually 8 Harry Potter movies because they split the last book into 2 separate movies because there was just so much story to it there. So there you go. So there's 5,040 different ways you can arrange 7 books. If you wanted to know the number of ways you could arrange the 8 Harry Potter movies, you would just throw an 8 in there and do 8 times all that. So interesting stuff. Notice again, no item is to be used more than once. For instance, if you have those 7 books and you put one on the shelf, you put, I don't know, Prisoner of Azkaban on the shelf, you don't have it available again to reuse. Now, there may be other situations where you can do that. Maybe if you're drawing cards from a deck and whatever card the first one is, you're going to put it back into the deck and reshuffle and just remember what the first card was. Then draw your second card, put it back, reshuffle, then draw your third card. That would not be this situation because you can reuse items in that situation about the cards. You can reuse items. But if you're talking about a permutation, you have to strictly only use each item no more than once. So we can introduce something called factorial notation. Factorial notation. Factorial notation is super important and valuable. Let's say we were getting tired of saying 7 times 6 times 5 times 4 times 3 times 2 times 1, because that is just a huge mouthful and cumbersome to say. We can actually use the exclamation mark. Now, that I'm not saying 7, like really loudly, like Jerry Seinfeld, 7. I'm not saying that. I'm not emphatically saying 7. I'm just saying 7 factorial. 7 factorial. So if n is a positive integer, the notation n factorial is the product of all positive integers from n down through 1. So n factorial is n times the one below it, n minus 1 times n minus 2, all the way down to 1. So 7 factorial is, well, start with 7, then multiply by the next number below it, then the next number below that, all the way till you get down to 1, and you'll get the 5,040 that we found last time. We make a weird definition. You would be tempted to say that if we could talk about 0 factorial, it would be 0. You would think it's that, but we make a little bit of a weird exception for 0. We say that 0 factorial is actually going to be equal to 1. 0 factorial is equal to 1. And you might say, what is that? You might like realize, why is that? Well, the number of ways you can arrange 0 objects is that you don't do it at all. The arrangement is just emptiness, but the emptiness is itself an arrangement. It is literally saying, here's the arrangement of all of the good, here's an arrangement of all the good Twilight books. There are no good Twilight books, so your bookshelf would be empty. So you've arranged all the good Twilight books on your bookshelf. It's empty, but you did it. You arranged it, if you will, by not doing it at all. It's kind of a weird thing. Also, I took a shot at the Twilight books. Sue me if you don't like it. Or don't. Please don't. We also are going to define 1 factorial also as equal to 1, although that one might make sense. But 0 factorial is also going to be defined as 1. So that's kind of wild that 0 factorial is equal to 1, but it makes a little bit of sense when you think about it in that context. So ultimately, n factorial is the number of ways we can arrange n objects, usually in a line or in a row. Something along those lines, something like that. So let's look at an example. Six people, and those 6 people will be Dr. Manhattan. These are superheroes. Silk Spectre 2, Rorschach, Night Owl II, the comedian, and of course, Ozymandias. These 6 people want to line up for a photograph. At the Crime Busters meeting in 1966. So they're going to take a photograph. These are 6 superheroes. And how many ways can they line up? Well, that's going to be exactly what the factorial is. It's going to be 6 factorial. You have 6 different objects. Now, yes, they are people. We're going to call them objects just for convenience sake, because they could be physical people or they could be just actual objects that don't have like a soul or anything weird like that. So 6 factorial is going to do it for us. It's going to tell us the number of different ways that we can arrange 6 objects in a row and how many different ways we can rearrange. Xavier said you loved The Watchmen. Oh, is this a reference to The Watchmen? Oh, I didn't even realize that. I just made up 6 names. No, these are the main characters from a series called The Watchmen. It is the only graphic novel, which is a fancy word for a comic book, is the only graphic novel that is generally agreed upon to be in the top 100 novels of all time. And we're talking about like heavyweight novels, like Crime and Punishment, or some Mark Twain, or there's all kinds of novels. Think about the great classic novels, the top 100. Most lists will include the Watchmen graphic novel along those. And it's the only one they'll do. And you better believe they will keep comic books out of that list normally if they could. They're like, no, it has to be an old book. It has to be Joseph Steinbeck or Ernest Hemingway. But no, anyway, so yeah, this is from The Watchmen. Great observation, Xavier. I was hoping someone out there would figure that out. At any rate, there's 720 different ways that we could rearrange the 6 people to be in this photograph. So kind of an interesting idea. So n factorial tells me the number of ways I can arrange n objects. Another thing is that you're going to want to figure out how to do it on your calculator. I'm going to verbally go through this. I'm going to verbally go through this with you. If you have the TI-30X2S, which is that standard, the gold standard scientific calculator that we sell here at the Weatherford College bookstore, and that is just the bee's knees. If you have the TI-30X2S, pop that bad boy out. And then what you want to do, and I don't have one in front of me, so I'm kind of trying to remember off the top of my head. What you'll want to do is if you want to calculate 6 factorial, hit in the calculator, hit a 6 on a clear, fresh line, hit 6 first, then hit the PRB button which should be kind of next to the log button. It's just down and right of the second button. Hit PRB and you should see somewhere, you might have to scroll left and right to the different sub menus, but you should see the exclamation mark, the factorial. Highlight that thing, hit enter, and it should bring the factorial down next to your 6 so that it's 6 factorial as you want. And then hit enter and the calculator should tell you 720. That's how you can find it on the TI-30X2S. But wait, there's more. In that same PRB menu, you should find NPR and NCR, probably just right underneath the exclamation mark. Those are going to be the general tools we use for permutations and combinations, respectively. And we will be talking about permutations and combinations today, what they represent. So very useful if you're on the TI-30X2S. If you're on the TI-83 or 84 graphing calculator, let me pull that bad boy up. If you're on the standard graphing calculator, let's see, let's find a good picture of it on the internet. The first thing you do is in a fresh, clean, blank line, type in a 6, then hit the math button, which is located just underneath the alpha and second buttons. Hit the math button, then scroll over to the right a couple spaces until you get to the PRB submenu. PRB stands for probability because all of this involves probability. You should find the exclamation mark. You should also see NPR and NCR. We will be using those later, but go highlight the exclamation mark, hit enter on it, and then it should bring the exclamation mark back to the home, the main screen with next to the 6. And it'll literally say 6 factorial. You can hit enter there and get 720. If that didn't help, or if you have a different type of calculator, what you'll need to do is you can calculate a factorial using the straight up definition. But if you had to calculate 13 factorial, then you have to, by hand, type out 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then hit enter. And it just gets cumbersome and you greatly increase your odds of making a mistake. So you'll need to kind of just Google it, type in the model number of your calculator and say factorial. How do you do the factorial? How do you do the permutation? How do you do the combination in my calculator? And type out the calculator model. You should be able to find a YouTube video. You should be able to find an online manual for that. And let me tell you, it's going to be really what you need. It's going to go a long way for you. Okay. So we learned about the factorial. Now, there are actually some interesting things that we want to do with this. There's some interesting things that we can do with this. So back to the whiteboard screen. Let's say you have 11 books that you'd like to put on a shelf, put up on a shelf. But the shelf only has 4 spaces available. How many ways can you pick 4 of your 11 books and then order them on the shelf? In other words, from your group of 11 objects, how many ways can you pick any 4 of them and then rearrange them on the shelf? How many different arrangements of those 4 objects exist on that shelf? Well, this, you're going to have 4 spaces on the shelf. And let's say all the books are about the same size. We all know that some of the Harry Potter books are much longer than others. But that's space 1 you have on the shelf. This is space 2. space 3, space jam, and space 4. Well, now for space 1, you don't have 4 objects you could put here. You actually have 11 objects you could put here. For space 2, you've already taken down one of those books and you have put it onto space 1. So now for space 2, you only have 10 objects, and then 9 and then 8 for spaces 3 and 4. So it looks like you're trying to do the 11 factorial calculation. 11 times 9 times 8, 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But you're going to run out of spaces. So you're only doing the first 4 things in the calculation. This is a permutation of 11 objects taken 4 at a time. In other words, from a larger pool of 11 objects, I am counting the number of ways I can choose 4 of those objects and also rearrange the 4 I've chosen. In other words, the order matters. Whoa, let that sink in for a second. You have a large pool of 11 objects, 11 books. You can only choose 4 of them. There are all kinds of ways you can choose any 4 of those books. Then, once you've chosen your 4 books, you also want to count the number of ways I could rearrange that group of 4 on the shelf. That is what the permutation does for me. That is what the permutation does for me. And so if I were to multiply this out, 11 times 9 times 11 times 10 times 9 times 8, you're going to get 7,920, 7920. This kind of looks like I did this. It kind of looks like I took 11 factorial, but then I cut off 7 factorial. And if you don't believe me, 11 factorial would be 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That would be the top value. On bottom, it's just going to be 7 factorial. And then it looks like what I did was I crossed out the 7s, the 6s, 5s, 4s, 3s, 2s, and 1s. And that just left me with the 11 times 10 times 9 times 8, which is exactly what it is. Well, I'll give you a little bit of a hint here. This is going to be the formula we used. We could write it as 11 factorial divided by 7 factorial, or you could write it as 11 factorial divided by 11 minus 4 factorial, which would have just become 7, and then you apply the factorial. So kind of an interesting idea. Well, it turns out that is exactly what's happening. In fact, that is the exact formula we're going to use for the permutation. If you have a larger pool of n total items, and you want to pick any r of them, where r is usually going to be a smaller number, never larger, we're going to define that as the NPR. And it's n factorial divided by, do n minus r first, then take its factorial. This is the number of ways we can choose r objects from a larger pool of n objects and also rearrange the r objects we choose. That's what the factorial is going for. Excuse me, that's what the permutation is going for. And we use NPR, P for permutation. So we are going to be using the permutation to make certain counts of things. So let's see how this would work. You and 19 of your friends have formed a business. So there's 20 total people in this business, you plus 19 of your friends. The group needs to choose 3 officers, a CEO, an operating manager, and a treasurer. We don't call them treasurers in an actual business. That's more of like a little fun club at school. But okay, I'll play along. And how many ways can those offices be filled? Well, think about it. First of all, you've got 3 positions. So from a larger pool of 20 objects, you need to count the number of ways I could pick the 3 positions. In other words, the number of ways I can pick a group of 3 objects from a larger pool of 20 objects. Then once I have those 3 objects and I've made them, now I do care about the ordering. Let's look at an image of that. The order matters here. Because once I've picked, I've got 3 offices I can pick here. You've got 3 different jobs: CEO, the operating manager, and the treasurer, aka the one who embezzles the funds to buy a beach house for themselves. Well, there's 20 different choices you can make for the CEO. Then there's 19 you can make for the operating manager. Then there's 18 for the treasurer. And this is not the same. Whenever I pick the 3 objects, then I have to know the number of ways I could rearrange those 3 objects to fill these roles. So the order matters here. Because the 3 roles are different. The 3 roles are different. Imagine I picked Jimmy, Susan, and Liz to be my 3 officers. So that from the 20 people, those are the 3 I picked. Then once I've picked them, well, we could do Jimmy as CEO, Susan as operating manager, and Liz as treasurer. But we can also reorder them. We could do Susan as CEO, Jimmy as operating manager, Liz as treasurer. Or we can make it this setup. Or we can make it this setup. So we need the permutation because not only do I care about how many different ways I can pick 3 objects from a larger pool of 20, I also care about the order of those 3 objects because they can fill those 3 positions in different ways. So I'm going to use a permutation. I'm going to use the NPR. 20 is going to be my P. R is going to be 3. If you want to do this on the calculator, and I highly suggest you do, the calculator actually does an entire NPR calculation for you. And it's also found in that PRB menu we've already looked at. So first, from a fresh, blank, clean line in your calculator, type in 20. Type in 20 first, that'll be N. Then go find that PRB menu. It could be under the math menu if you're on a TI 8384. It could just be its own separate PRB menu if you're on the standard scientific calculator. But go find that PRB menu, and now that you've already typed 20 in, go highlight and hit enter on the NPR tool. When you hit enter, it'll bring it back to the main screen. So it'll say 20, then it'll say NPR. Then you can type in a 3 and hit enter. And it'll do this computation for you as 6,840. So there's 6,840 different possibilities. So that's how a permutation works. So the last thing we're going to look at for this section We're talking about what if you have duplicate items and you have multiple. So let's say you're looking at the word Mississippi. You're looking at the word Mississippi. M-I-S-S-I-S-S-I-P-P-I. There's an old way you can remember to spell it. What if we wanted to count the number of ways we could rearrange the letters in the word Mississippi? Now there's 11 total letters, but if I rearrange just the I's, if I move just the 4 I's around and leave everything else the same, then the word's not going to look any different. Whatever new thing we create is not going to look different. So we run into this problem if we have repeated entries or things that have multiple occurrences of the same value. So if I were to rearrange the 2 P's and switch them, it doesn't matter. It doesn't change the way the word would look. It doesn't change if I change the 4 S's around. It doesn't matter. So there's 11 total letters, but 4 of the I's are identical. 4 S's live in Texas, they are identical, and 2 P's are identical. So what I would do is to find the number of ways of rearranging them, I would take the 11 factorial, but I wouldn't just leave it at that. I would divide out by 4 factorial, the number of ways of arranging the P's. I would divide out, the I's. I would divide out by another 4 factorial, the number of ways of arranging the S's. And then the I's. Wow, I'm really screwing up here. And then by 2 factorial, the number of ways of rearranging the P's. So it's a pretty simple formulation. Nothing too wild going on. And we end up with 34,650. If you just did 11 factorial, you'd end up with a much larger number than that. But you have to divide out by the fact that rearranging just the S's or just the P's or just the I's don't do anything because they are identical. This is called a multinomial. Sometimes you'll see it called that. And that's all there is to it. Pretty straightforward process. The next section here is over combinations. So we've looked at factorials, which just involves that exclamation mark. And a factorial tells me the number of ways that I can arrange a certain number of objects. Permutations, that's also the same idea, but permutations also let me just pull from a larger pool of objects and make a number of subgroups of a certain size. But in a permutation, the ordering or the arrangement, the number of arrangements of those objects matters. The only difference between a permutation and a combination is that for a combination, the ordering of the objects doesn't matter. It is irrelevant. So a combination of items occurs when the items are selected all from one similar group. No item is used more than once. You can't reuse the same object. It doesn't make sense. But also the order of items does not make a difference. That's the key. The order of the items makes no difference. So the major difference, again, a permutation and a combination are both all about this. Take a large pool of objects and count up the number of groups of a certain size you can make from that larger pool. The difference, though, is that a combination, the order of the objects, once you've made the smaller group of them, the order doesn't matter. For a permutation, it does. So for instance, think back to that problem we did where there were 20 people in a company, and we wanted to count the number of ways we could elect some people to be CEO, to be the operations manager, and to be a treasurer. Well, that was a permutation because the roles of CEO, operations manager, and treasurer are all distinct and different. So the order of the group of 3 matters. But let's say I had a company with 20 people and I was going to make a committee of 3 people to investigate a certain matter. The number of ways I can make that committee now would actually be a combination, because once I've chosen the 3 people from the pool of 20, I don't care about the number of ways I can order those 3 people. So let's read out this problem, decide if a permutation or a combination is appropriate in this case. 6 students are running for student government president, vice president, and treasurer. So now treasurer might make sense in a little student government thing. The president with the greatest number of votes, the student with the greatest number of votes becomes president. The second highest vote getter becomes vice president, and the third highest vote getter gets to be the treasurer. How many outcomes are possible? That would be a permutation. We're not actually going to calculate it, but that would be a permutation of 6p3. From a pool of 6 objects, we want to know the number of ways I can select any 3 of them, and also rearrange the 3 people or the 3 in that smaller group, because there's 3 distinct roles of president, vice president, and treasurer. 6 people are on the board of supervisors for your neighborhood park. A 3-person committee is needed to study the possibility of expanding the park. How many different committees could be formed with the 6 people? This is a combination, not a permutation, because the 3-person committee, everyone is the same role. They're just different people in the same role. Everyone is just a stock committee member. They don't have any other special designation beyond that. You don't have 3 separate roles. Thus, the way I can order the group of 3, once I've chosen them from the larger pool of 6 candidates, that order doesn't matter. So that's the major distinction. Permutation, order matters. Combination, order does not matter. And that's what you got to know. Now, we haven't even yet talked about the formula for a combination, but we will here very shortly. And it's similar, but not exactly the same as the formula for a permutation. So let's say you have the letters A, B, C, and D. We can compare the number of permutations and combinations that are possible if we choose 3 letters at a time. So if you think about it, there's only 4 possible ways you can choose any of them. You can choose A, B, and C. You can choose A, B, and D. You can choose A, C, and D. Or you can choose B, C, and D. If you didn't care about the number of ways you can rearrange them, these are the only 4 possibilities. If you didn't care about the number of ways you can rearrange the 3 letters once you've picked them, these are the only 4 possibilities. Because if you pick A, B, C, you only care, hey, did I get A, B, and C in there? Great, I'm done. But in this column, we're also going to include the number of ways you could rearrange those 3 letters once you've gotten them. These are the number of ways you can rearrange the letters A, B, and C. So if you're just looking at this column in green, this is a combination. In fact, it's 4C3. Take a pool of 4 objects, choose any 3 of them, and you'll see that comes out to be 4. So C for combination. But if you care, in red here, if you care not only about how many ways you can choose the 3, but also how many different ways you can rearrange the 3 objects once you've chosen them, you care about all 24 of these, including the top row. So in red, In red, we have all the possible permutations of size 3 from a pool of 4 objects. Here, we care about the order the 3 objects can take. This will be a permutation, 4p3. If you do that in your calculator, you'll get 24. So that's a cool little graphic that shows the major differences between the two. We can look at the combination formula. If you have n objects, take an r at a time. It's this formula. It's very similar to the permutation formula, except we are also throwing an r factorial here into the denominator. That's the only key difference. So this tells me the number of ways of choosing R objects from a larger pool of N objects. And once I've chosen the R objects, I don't care about how many ways they can be rearranged. Slash ordered. That's what a combination does for me. So that's a combination. A permutation does care about the ordering of the smaller pool of objects. That's exactly what a permutation is trying to count. So how many 3-person committees could be formed from 8 people? So we have a pool of 8 objects. We're trying to pull any 3 of them. Once I have the 3, we're just going to assume that everyone is the same thing, a committee member. You don't have 3 different roles on it. So it's 8C3. The formula would turn into this, and you'll end up with 56. On your calculator, you need to figure out where the factorial, the NPR, and the NCR menu is. You should have all of them pretty much near each other in the same menu. And to calculate this, you would first put an 8 in. You would clear out a nice fresh space for an 8. Then go find your NCR option under the PRB menu, most likely. Hit enter on that. It'll bring NCR back to the screen after the 8. Then type in 3 and you'll have 8 NCR 3. Hit enter and it should be giving you 56. So there are 56 ways I can pick 3 objects from a larger pool of 8 objects. Another one. In December 2011, the U.S. Senate consisted of 51 Democrats and 47 Republicans, as well as 2 independents who are in neither party. How many distinct 5-person committees can be found if each committee must have 3 Democrats and 2 Republicans? This one's actually going to be kind of interesting. So we want a 5-person committee. Now, if we were able to choose any 5 people from all 100 US senators, if I add 51 plus 47 plus 2, that gives me 100. Although you should probably know there's 100 US senators because there's 2 from each of the 50 states. If I didn't care about the breakdown of the group, then I would just do 100 C5, 100 NCR5. But now I do care about the breakdown. I want my group to have exactly 3 Democrats and exactly 2 Republicans on it. So we actually have to do a couple of things. Since we can pick any 3 Democrats out of the 51, and imagine 51 different names, and we're going to pull any 3 of them to be the 3 Democrats represented in our committee. I need to do 51 C3, which will give me 20,825. But we're not done. We also have to pick 2 Republicans from the larger pool of 47. So we also have to do that. Select 2 Republicans out of 47. We need to do 47 C2 using the NCR thing. So 47 C2, you can do the math. You can use your calculator tricks. You'll end up with 1,081. So there's 20,825 ways we can pick the Democrats. There's 1,081 ways we can pick the Republicans. We're going to end up multiplying those numbers together because you could think of this like this. I've got 2 things I have to do. I have 2 tasks. First, I have to pick 2 Democrats. This is my first task. Pick 2 Democrats out of 51. That's going to be the first task I have to take on. That doesn't look any better. Then I have to pick 2 Republicans. I'm sorry, I picked 3 Democrats out of 51. That was the key number. I have to pick 3 Democrats out of 51. Then I have to pick 2 Republicans, basically out of 47. Let me clean this up a little. So task 1, pick 3 Dems out of 51 available. Task 2, pick 2 Republicans out of 47 available. Each of these individual tasks, we have to use a combination to calculate. Then we multiply them together to calculate the number of ways we can do both tasks. So not so bad. Let me pull up a few homework assignments, a few homework problems from chapter 11. We'll work together and then we'll call it a day. Now, your chapter 9 homework and the first 3 sections of your chapter 11 homework are all due Thursday night, same day that your exam is due. So just keep that in mind. Remember, to access the exam, you need to look at the exam 3 instructions in Canvas, in the exam 3 module. That will be what you must do. So let me pull up a homework problem for you. Let's see if I can find a difficult one. Okay, I'm going to do from a homework section 11.2. Well, heck, I'll just show you. I'm doing number 18. Now, the numbers you get in your problem might be a little different than the one I get, but the same basic structure is there. In a race in which 8 automobiles are entered and there are no ties, so don't worry about ties, in how many ways can the first 3 finishers come in? Well, we're picking 3 objects from a larger pool of 8. We're picking 3 objects to be our top 3 finishers from a larger pool of 8 automobiles. So we're either doing a permutation or a combination. Does order matter here? Yes, because we have a first place a second place, and a third place. So the order does matter because they can, there's the three we're picking from the larger pool of 8 do have distinct positions. So this is a permutation, 8p3. You can go put it into the calculator, do your 8p3, you should get 336, not with a bracket. So a lot of these are going to be, the difficulty stems from deciding whether it should be a permutation or a combination. Use some logic to parse it out and then act. Sure. Number 20 now, we have to be really careful with number 20 because, oh, we see the word readers. There's 1, 2, 3, 4, 5, 6, 7, 7 letters. So how many different ways can we arrange 7 letters? You're going to try 7 factorial, which is 5,040, and say, okay, it's 5,040, and now I can go home and I'm done for the day. Wrong. The reason is that notice you've got 2 R's in there, you've got 2 E's in there. Then you have a single A, a single D, and a single S. But basically, if I were to rearrange the R's, it wouldn't change anything. If I were to rearrange just the E's, it wouldn't change anything. So I need to divide out by the number of repeat R's, which is 2, and then factorial, and the number of repeat E's, which is 2, and then factorial. So that's actually going to give me 5,040 divided by 2 times 2. 5,040 divided by 4. And what's that going to be? 1,260? Let's see if I'm right. I did that entirely mental math, and I was right. Cool. So remember, this is that multinomial case we went over when we were talking about like the number of ways we can rearrange the letters in Mississippi, because there are repeats that creates problems. Think about how many distinct permutations can be formed using the letters in the word programming. Well, there's, let's see, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total letters. So we are tempted to just say it's 11 factorial and then be done with it. But there's some repeated letters. Let's see, there's only 1 P, but now we're going to put the repeats. There's 2 R's, I think is all. There's no repeated O's, but there's 2 G's. There's just a single A. There's 2 M's. There's only 1 I, and there's only 1 N. So we're good to go. So this one's going to be 11 factorial divided by 2 factorial times 2 factorial times 2 factorial. Now, 11 factorial is going to be a huge number, but we're going to be dividing it by 2 times 2 times 2. 11 factorial is 39,916,800. But we're essentially dividing it by 2 times 2 times 2. 2 times 2 times 2 is 8. So that's going to be equal to a little bit less, but still a lot. There's going to be 4,989,600 distinct permutations, distinct rearrangements. Let's look at a few combination problems. See what we can get away with. Let's look at some combination problems. Let me see if I can find a nice, interesting one. Here we go on this one. You volunteered to help drive children at a charity event to the zoo. Why? Oh boy, you must really love your life. Taking 6 children in your car. Of course, I'm a master disciplinarian, so they will all be silent in my car. But that's probably just secretly because they're all on their phones. Because in this day and age, everybody is just always constantly on their phones at all times of the day watching TikToks, especially at that age. But anyways, you volunteer to help drive children at a charity event to the zoo, but you can only fit 6 of the children in your car, in your van. How many different groups of children, 6 children, can you drive? Here we're going to say we don't care about the order of the group of 6 once we've pulled them from a larger pool of 15. Because they're just going to plop into the van. Who cares about how they're arranged? You might care, so it just depends on the context of the problem. But here I'm going to assume, especially it says how many different groups of 6 children. It's not saying how many different ordered groups or something like that. It's seemingly implying that it's just a combination. 15C6. Now I'm also going to have to use my calculator that I have access to in order to calculate that. Let me do that real quick. That's one I'm not going to do off the top of my head. And the answer is going to be a stout 5,005. 5,005. Again, we're going to use a combination, not just because the homework says it's the combinations homework. That's nice when you're on the homework. On the exam, you're not going to know that. You need to reason for it. Let's see. Let me find one I think can be interesting. In how many ways can a committee of 3 men and 2 women be formed from a larger group of 7 men and 9 women? So let's think about it. We want a committee that has 3 men and 2 women, so that's 5 total people on this committee. We have 7 men available and 9 women available. So think of it as 7 men. You could have John, James, Mike, Steve, I don't know. I can't think of guy names right now for some reason. But think of it as you have 7 distinct men, and you want to know the number of ways I can have any 3 of them to be in the group. So we have 2 tasks. Task 1 is going to be choose any 3 men from the larger pool of 7 men. That's our first task. Our second task is to pick choose any 2 women from the larger pool of 9 women. Each one of those tasks is going to involve a combination. This one will be 7C3. This one will be 9C2. We're going to end up multiplying them together, but first, let's calculate each of them. 7C3, yeah, just use my calculator. I'll be lazy. I get to be lazy. 7C3 is going to be 35. The 9C2, I want to say, is going to be 36. Let me double check it. Yeah. And so we just need to do 35 times 36. $35 times 36 is 1260. So there's 1,260 different groups I can make that will have 3 men and 2 women when I'm pulling from a larger pool of 7 men and 9 women. Let's try out one more. Let's see if we can find a nasty one. This one's actually kind of interesting. We won't work it fully. But in a race in which 12 automobiles are entered and there's no ties, how many ways can the first 3 finishers come in? This one is interesting. We're just going to, instead of saying first place, second place, third place, it's just saying, well, as long as you're in the top 3, you're a finisher in the race. You might see that in races where you don't care who finished first, second, or third. You're just saying the top 3 go on to the next race. You might see that case. This now would be a combination of 12C3. Because from a larger pool of 12 objects, I want to know all the ways I can pull any 3 of them, and then I don't care about the order of the 3 objects once I've done that. Let's see if I can find a real nasty one. Using 11 flavors of ice cream, how many cones with 3 different flavors can you create if it is important to you which flavor goes on top, which one goes in the middle, and which one goes on bottom? That might be important to you. You're like, I will not eat, my strawberry chocolate vanilla swirl fudge thing if chocolate comes first. That disgusts me. So here the order does matter. So just because it's in the combinations section, it's kind of tricking you. Order does matter. So now from a larger pool of 11, we're going to do a permutation of 3 objects. Notice that it says 3 different flavors, meaning you can't get 2 scoops of strawberry and then 1 scoop of vanilla, or you can't do all 3 scoops chocolate. You have to have 3 different scoops. If you could have repeated scoops, you can't even use a permutation or a combination. So that's going to be 11P3, which should be 990. Let me double check that. I think I made a mistake. Nope, I'm right. 990. So just because it's in the combination section, it can be a permutation. It's, in fact, these are literally designed to kind of trip you up and make sure you're paying close attention. Okay, that's it for today.